Niels Bohr took Planck's quantum idea and applied it to the electrons in atoms. In other words, Bohr said, if electrons can only have certain amounts of energy, then electrons can only be found at certain distances from the nucleus. The Bohr model of the atom, which has a nucleus in the center and rings, you might say, of electrons, Bohr said, hey, if electrons can only have certain amounts of energy, then we're only going to find them at particular spots, and we'll never find them in between those spots. That's the basis of Bohr's planetary model. Bohr assumed that the electrons in his circular orbits had particular energies that were given by this equation, where the energy of an electron in the nth energy level, that is with a principal quantum number of 1, 2, 3, and so on, is given by this equation, where R sub h is called the Rydberg constant. It's simply a number. As you can see from the equation, the electron with respect to the atom is assumed to have negative energy. In other words, you can't do this calculation and not get a negative number for an electron's energy with regard to that atom. The more or less negative that an electron's energy is, the more or less stable that electron is. So you can see from this equation, basically RH is just a constant, so that's just some number. So what we have here is the energy level squared in the denominator. If we put a 1 in for n, we've got 1 over 1. If we put 2 in for n, we have 1/4. If we put 3, we have 1/9, and so on. And as we go from 1 to 1/4, this fraction to 1/9 to 1/16, and so on, you can see that the overall number is becoming less and less negative. That is, it's creeping closer and closer to 0. This statement here, the more negative an electron's energy is, the more stable that electron is, because that electron is in a lower energy level. And if we reread the statement and use the underlined words, the less negative an electron's energy is, the less stable that electron is. If we visualize this with an energy well, this electron, let's say, has a very negative energy. That electron is very stable. It's in one of the inner energy levels, let's say. If we have another electron that is a bit negative, bit of a negative energy, well, that electron is a bit stable. And if we have another electron that has a barely negative energy, in other words, it's just below 0, it's barely, if at all, stable. In other words, that electron is very easily lost. So, when n, which is again the energy level, or the principal quantum number, when n is very large, E sub n goes to 0, which is the most energy an electron can have, because 0 is larger than anything negative. That is, when n equals infinity, the electron has escaped completely from the atom, and with respect to the atom, that electron has no energy. Bohr stated that electrons could move from one level to another, absorbing light of a particular frequency to jump up, and releasing light of a particular frequency to fall down. This is, in essence, Bohr's explanation of line spectra, hydrogen, the absorption and the emission spectra. For hydrogen, there are only discrete lines that are evident, and this is Bohr's explanation for that, that electrons can only have certain amounts of energy that are allowed in order for them to jump up to particular higher energy levels or to fall down to particular lower energy levels. For example, just to illustrate this point, we're not going to use hydrogen here, we're going to use helium, which has 2 electrons in the 1s orbital, and what we're going to do is we're going to put some energy into that atom. Watch what happens when we do that. Boop! One of those electrons jumped up to a higher energy level. Now, it could be any higher energy level. Just to keep things simple, I'll say that it jumped up to the 2s orbital. That is an unstable situation, and so what will happen is that electron is going to tend to want to fall back down, and when it does, watch what happens. It's going to release energy as light, and that light is going to go off, and we're going to be able to observe it. Bohr's model, that is its specific equation, the one on the previous slide with the Rydberg constant, worked only for atoms with a single electron. And this is of course a bit problematic because most atoms have more than one electron. Clearly there is more work to be done, but Bohr's model was a stepping stone along the way. Final thoughts on the Bohr atom conceptual. 1. Bohr took Planck's quantum idea and suggested that it might explain the distinct bands of color in the line spectra of hydrogen, namely that electrons release or absorb only certain amounts of energy and are thus stable at only certain distances from the nucleus. 2. Bohr said that an electron moving in a circular orbit in the nth energy level of a hydrogen atom had an energy given by this equation in yellow, where R sub h is this number right down here, and it's called the Rydberg constant. And 3, according to Bohr's equation, when n equals 1, the energy of that electron is in fact equal to the Rydberg constant, negative 2.18 times 10 to the negative 18th joules. When n equals infinity, that is when that electron has completely escaped from the atom, the energy of that electron with regard to the atom is 0 joules.